Alright, time for another draft physics video presentation. Comments, and then maybe we'll move on to another subject. Interesting. Charge and magnetism. Yes. Anyway, lots of little details. But anyway, let's see if we can get through this first. So, Dave seems a nice enough sort, but I don't know. What a cool picture. At first glance, I felt like I was still stuck in my little tin can, but a few more, and I suppose it meant to resemble anything from a well-balanced, I don't know what that is, victim, to a bunch of Arabs magnetized towards Mecca. Okay, oh, there's more. Anyway, time to shut the fuck up. Yes, there you go. Thanks ahead. Well, that's always dangerous. So yes, really, commenting should be done after the video is completed. Thank you very much. I'm an anti-magnet when I go to a chat room. Ha ha. Well, don't know what to say about that either. Yes, this isn't really what I'm looking for. Thanks, but no thanks. So, yes, it's an interesting picture of a magnet in the background sometimes. Yes. Art or whatever. But unlike Professor Lewin, I don't think there's any point in mixing art and physics. So let's not talk about what looks interesting. Let's talk about if we can understand how things work. Yeah. Alright, anyone can sit there and criticize someone. Well, that's really not the point, and the criticism's really usually supposed to be directed at, getting to something, getting to a truth, and unfortunately nobody can ever stay on one subject and properly beat it to death. So everybody just keeps bouncing around, arguing the same stuff in some circular pattern, and it's just quite nauseating. Just debate him. Okay, I don't know why you're saying that on my video. I mean, obviously he isn't paying any attention, so you need to say that on his video. Yeah, Ken is so confident he can destroy people, then he wouldn't be a coward to debate. Yes, you say that on his video. I've already said all of this stuff, yes. Does anyone have any links to Ken debating someone? Well, of course nobody will have any such link. Alright, hey Gary. Not sure if you have mentioned it before, but a good demonstration of how to get the illusion of curved field lines. I'm not looking for curved field lines. The point is that the lines are something matter does. It's not something the field does. So again, the fields don't interact with the fields. They can only interact with the matter. So, and the real point is that the illusion that there is a force that is curved is an illusion. None of the forces are ever curved. They are in some r squared or r factor affecting an object at a distance with a straight line force. The point is, a straight line force explains all the curved lines. Anyway. Curved field lines from a pattern of dots in a frequency. Now, you're heading way wrong, this frequency thing. Dots and frequency probably isn't going to work. Is a Mori pattern. That's, remembering my Professor Wizard thingy, Mr. Wizard. Yeah, that's what watered silk. Okay. You can also see the same effect if you take a photo of a TV screen or a computer monitor. Great videos, thanks. Now, it's not the same effect because there's a grid in front of the TV screen that's forcing the photons to hit a grid of phosphorus. So there's two grids. Anytime you mix two grids, so you have this, and then you superimpose this on it, okay, you're creating two obstacles that this light has to go through. And you can sort of understand that if I turn this one, oh, fuck, look at all these surfaces I'm creating. And then you can see that the surfaces aren't smooth surfaces. There's corners in the surfaces, little corners. And obviously electrons would hate little corners. They don't want to be in corners at all. So the pattern is being created because the electrons will, because of the straight line forces again, be obliged to move into positions that aren't proportional to where they were. So you could sort of understand that if you did have a square, right, which I created by having two grids placed on top of each other, and if I, like even screen, you could put screen on top of screen, then turn the screen, and then what you're doing is putting the squares on top of each other this way, so you're creating even more little surfaces and more little corners. But you can understand that if I put electrons in this box, the electrons all want to go to a comfortable place, and the last place they're going to end up is in these corners, right? So we're saying this is a negative surface. So they don't like the surface. Well, they really would hate this surface because the two lines would be very short, and this would be a very unpleasant place for an electron to hang out. So they would tend to move out of the corners. So you'd have no electrons in corners, and the corners, and so you have all nice straight lines, but what you'd end up with is electrons that would fill this gap with a curve, and they'd fill this gap with a curve, and they'd fill this gap with a curve, and they'd fill this gap with a curve. So you'd have the illusion of creating a circle out of a square, but it's still all straight line force. Technically, that's creating the illusion of the circle inside the square. All right. I don't know if there's a whole bunch of, I don't know if it's an interesting subject of, how do you, every time you create a surface is the point. This surface thing is so important, distinguishing the two slit or the single impediment and recognizing that what they have in common is slits at exactly the same distance. Surfaces. It's all about the surfaces, and that if I make a thing smaller and smaller, I'm increasing the likelihood of the photon traveling next to the surface. It's the surface that makes the photon go loopy, because there's electrons there, and photons, when they hit electrons, don't move straight. Well, they do move straight from their point of view. Again, if you're by this corner or you're here, you're going to move straight in a different direction depending on the forces that are binding you, how even they are. If there's two forces holding you, one this long and one this long, right? So you got two different size forces holding you in a position, and something force hits you. Obviously, the fact that there's a stronger force on this side than this side will mean you'll have to go, you'll be bent by that stronger force, will have more influence on your trajectory. You won't have a nice straight trajectory. Alright. Good video, thanks. Well, I guess I'll accept that one. So Mike Wyul, long time no converse and such, but ha is not very useful, so yeah, sorry. I'll just take a pass on that one. It's not very scientific. So Qantas doesn't really do me any good either. It's like, what, an Australian joke or something. Deepak Chopra springs to mind. Well, I just don't really care. It's not enough of a directed comment. Say something like, Piro might as well be a disciple of Deepak Chopra, but just saying it, somebody could take that comment the wrong way or something. I don't know. Just stay away from that kind of crap. Obviously, it's all seems like a frickin' religion is what it sounds like. Conventional physics, when defended especially by the loopers, does sound like a religion. Alright. In the particle at the end of the universe, who cares? Sean Carroll, that's the part I meant to say, who cares after, because yeah, who cares? Sean Carroll believes in multiverses as a rational solution to a problem. Oh, we have a problem. We have to figure out why something's doing something. Let's just invent new universes, and then everything can happen everywhere. I mean, it's just too silly. Says matter is really waves. Well, lots of assholes say this crap, and it's stupid and ignorant, and it's so assumptive. I mean, there's just no reason. You don't need to believe this crap. It doesn't look like a wave. It doesn't behave like a wave. There's no waves coming out of a magnet. I mean, anyway. But when we look at it carefully enough, we see particles. Well, gee, isn't that silly of him? And frankly, wouldn't you see it the other way around, right? You're just basically saying, if you want to find some waves somewhere, we'll find a whole bunch of particles, and they might be waving. Because particles can look like waves when there's a whole bunch of them. Duh. I mean, you know, theoretically, the crap that's coming out of my mouth, right, the waves of sound, you know that they're made out of atoms that are moving. You know, that atoms move, stop moving. Atoms move, stop moving. Atoms stop, you know, they bang into each other. We know the atmosphere that's providing the medium for the waves of sound. We know that medium is made out of little atoms. So, you know, the theory that particles can make something look like a wave is obvious. Anyway, he would fall into the wave camp along with Sabine, it seems. Well, all of physics is fallen into it. So again, they don't believe in any wave-particle duality. Again, Professor Lewin uses words like, it's nail-in-the-coffin evidence that light is a wave. And then he'll talk about wave-particle duality as if that's a principle they believe in. You can't have it both ways. They've clearly decided it's waves. They've clearly decided it's ether theory. But they're afraid to say the word. I mean, they're just so full. They're full of shit just because of these dishonesties. Again, they never fixed plus and minus. I mean, a gross error, and they never fixed it. Well, I guess I don't know. I hate to leave crap comments, but whatever. All right. Simple mechanical model and baseless accusations. ... Miserable. ... Just give ABCs why this can't be right because I hasn't heard any so far. See, this is a problem with comments. It's just, this comment could be read by somebody as being, you're complaining because I'm somehow giving baseless accusations. You know, he's actually agreeing with me, I believe, you know, but he's not doing it very well. So exactly, so Dave answers and says exactly what can't be right. So he thinks he's saying I am saying something that can't be right. See, I mean, you commenters, you need to be a little bit more, you have to extend a little bit more effort. You know, I do, you know, go the extra mile and I draw pictures and stuff, you know. Sometimes you have to go a little farther to make sure your comment is going to be understood. All right. Always puts me backwards. Can you do a video on this new little magnetism experiment? Nature's Secret of Magnetism. So this is fucking Ken Wheeler crap, you know. And you're just, what, you want me to debunk every single one of Ken Wheeler's wacky and stupid and moronic videos? Well, no, I'm not going to do that. I mean, either make an argument or don't comment. Okay, and the arguments have to be on a specific subject. You have to make an assertion. They've proven ether, or I've proven a hyperboloid, or something. And you have to assert it with a citation to some sort of evidence. I mean, this vague crap is, you know, could end up being such a waste of my time. I'm the one who has to do all the research, you know, to answer a phenomenon for which there's no phenomenon because you read it on whatever, the Flintstones homepage on Facebook or something. because Fred was really interested in some stupid little thing, the world should stand still and say, wow, what a great, brilliant phenomenon. No, it doesn't really work that way. Alright, so, technical issues either on your end or mine. Well, I'm sure it was your end, so you probably should have removed your comment. Thank you very much. The video is fine. Should have removed it. Sheesh. Alright, Dove. So there's a Dave and a Dove. Gee, that makes things a little bit complicated. Alright, I have to keep them, remind myself. Oh, it's a different guy. I made a simulation to explain photon inverse square law so that some viewers can understand it visually if they can't follow. Well, I drew a picture of it. I mean, it's a really important picture, and frankly, it's the best way to understand it, frankly. That, you know, it's an area argument, and that's all it is. It's just about the fact, just like a circle, when you take a circle and you make a circle twice as big, that is twice the radius, you know, that you get a much larger circumference, okay, that it's not just twice the circumference anymore on a sphere. And the inverse square law is just telling you that, you know, you could just draw these lines. I could draw them very well, or I can draw them not so well, and that there's a square. Okay, so if I draw 4 lines representing divergence in 2 directions, that is, it's going this way and it's going this way, and it's spreading in both those directions, that you could draw the square at half the distance. And this isn't going to look exactly right because I didn't draw it exactly right, but the point is that at half the distance, this square is 4 times bigger, this area. Okay, so, and again, how, you know, the easiest illustration is just to do this with my hand. Just point out that, okay, my hand here is 4 times bigger than my hand here. So light's doing exactly the same thing, and it's being created by straight lines, diverging, forces diverging, rays diverging. But whatever. Yeah, your simulation was completely, I can't see it, so, you know, I mean, I'll go to it, but there's nothing here. I mean, I made it bigger, and I still can't see the dots. There's some little thing going blip, blip, blip here, and then there's just this. So, it didn't work, sorry. Thank you, though. I mean, thank you for trying. But obviously you should just said, obviously slow down so you can track each particle with your eyes. Well, obviously I can't track any of the particles with my eyes. Each particle has the same velocity. Well, they really should. Wait, so you say this is a simpler way to understand the inverse square law, simpler than this. 4 times bigger. I don't think it's simpler. But whatever. Alright, Zohar. So you're saying the neutron is spinning very fast, which is making it seem neutral. Whether it's spinning or whether the electron is rotating around the proton, it doesn't really matter. The point is that the proximity of the plus and minus, the idea of it is that it's spinning. It has a blue end, let's say, and a red end. And if it spins fast enough, I'm just going to see purple. That's the simple principle. So yes, the neutron is just a hydrogen atom where the electron isn't out here in space. It's right on the surface, let's say, of the proton, and it's just rotating around the surface of the proton. So it's smaller than the hydrogen atom. So unlike hydrogen, it's really dense. So if I had a neutron, it would just sink. And if I had a hydrogen atom, it would float. And the only difference is the space. Okay, I mean, I could definitely draw that one, right? And you could argue that there would be an energy to these objects based on this proximity law. So again, so the idea is you just have a proton here, and the difference between a neutron and a hydrogen atom is just how close this electron is to the surface. So in hydrogen, It's obviously pretty far away because this atom floats. It's buoyant. It has more empty space in it. See how much empty space you have in you, how much air is in your submarine, you know, how much free air, uncompressed air, decides how buoyant your submarine is. And the same is true for atoms. So how light the atom is really, because they're all made out of the same little bits, it's just how much space per electron and proton. So the neutron has very little space. That's why you can get a whole bunch of these neutrons clogging up inside of something called a neutron star or something, and there's very little space in there. No space, right? So no space means heavy. Okay, small thing, very massive. This is probably the only thing there is. Neutron stars. Just not black holes. Black holes is bullshit. Anyway, but regular matter, it can't do, you know, hydrogen isn't going to allow you to do that. Now, I suppose I would argue that when hydrogen does do certain things, it does maybe get a little smaller, like hydrogen 2, you know, and then when it's in an atom, you know, when a hydrogen atom goes inside of a molecule, it probably decreases in size a little bit, and that would be the energy differential of releasing a hydrogen atom from and binding an atom. So the process of binding the hydrogen collapses the atom a little bit, and then the process of releasing it expands it a little bit, blah blah. That's the extra energy. That's what they call neutrinos, and all this other crap that they've called stuff isn't really stuff. It's just the extra amount of force that gets released in terms of the pressure between the electron and the proton, and the mechanism that's binding the electron to the rest of the universe. See, there's other protons in this electron's universe, and so it binds to them. That's why hydrogen doesn't like to be a single hydrogen atom. It likes to be bound to another hydrogen atom. Well, anyway, I don't want to get into all that. Alright, do electrons orbit the neutron then? Orbit is not a useful word, I don't think. If you're saying that the electrons are attached to the neutron, you know, probably, maybe, I think I'll agree with you. Well, I don't really care one way or the other. I mean, it's all just speculation, frankly, at this point. But I know electrons have orbital levels. You can say you know that. See, this is another thing that's just kind of commonsensical if you understand what's holding electrons and protons together. The idea that they would have standard orbits is like a duh. Like, duh. So if I did make it out of magnets, and I said, here's a south end of a, you know, I had magnetic monopoles. I put a south end here, and the little north end is the electron, right? And I established that, okay, whoops, there's other little norths here, okay, because I created this inside of a sun, and I arranged these little fellows, and so this is their arrangement. Now you could understand that the tension, the repulsive forces, would balance the attractive force to the proton. That this electron, I mean this end face, couldn't get any closer to these two, okay, without creating extra pressure this way. So the force preventing it from going to the south end is the repulsive force, because it has to get closer and closer to these electrons, and they are not going to like that. Blah 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 blah. So they push back. So everything stays stable in this configuration. Now, if you believe the electrons are a standard charge, just like the magnets, so it's a magnetism of one, and they all have the same magnetic potential, then you could understand that these distances are obligatory, and that the next, if I was to have more electrons attracted by this nucleus, that where would they be? Well, the next electron would be here, and the next electron would be here, and the next electron would be here, and there'd be a standard amount of pressure between these, because this pressure is going to be a little bit less, this distance will be a little bit more, but you can get the idea that they're going to line up commensurate to the pressure, and they're going to have specific places that they can be comfortable, and so on, and so on, and so on. So the ones in here are going to be close together. The ones out here are going to be further and further apart. and there's going to be a standard distance that you could draw it as an orbital, but I mean it's going to be a standard distance because the charge is a standard charge. So that's why there's orbitals. Simply put, nothing could stay here. It's an uneven amount of charge. There's either too much attraction to the proton or too little or too much repulsion from the other electron. So nothing can go in these gray areas here. It has to be either here, here. It has to be in a certain geometry. So I'm just saying the magnetic model of the atom explains why there's specific orbitals. All right. So I'm also inclined to agree that they could orbit around the neutron and are attached to the neutrons only through the gravity mechanism. Well, I don't even know how you could go there. There's no gravity on this level. Atoms don't do gravity. They do charge. They're electrons and protons. They have no gravity. All they care about is charge. There's no such thing as gravity from their perspective. There's only I'm a negative or I'm a positive. That's it. Oh dear. Anyway. Through the gravity mechanism, since it's neutral. Well, there's nothing neutral inside of atoms. I'm just pointing out. It's clearly what keeps an atom stable is having a balance between the number of charges, and so it's all about the charges. But there's no evidence for an I don't know where that comment went, or that word went, for that, and it also somewhat makes sense to say they're attached to the neutron in the same way a neutron, electron, and proton are attached to each other. Well, whatever. Sadly, I don't think you're really getting some of this stuff, but whatever. Mush on. That starfish name from SpongeBob is Patrick. Yeah, okay, I knew. I mean, unfortunately, I asked for it. By the way, then we have Zohar. The irony, considering your last name is Kohevi, which is, if I remember correctly, means starry in Hebrew. So we're doing derivatives of people's names. I think we can just do without all this. Ugh. Yeah, sorry. I'm really interested in doing physics. Just really not interested in all these other subjects. The time dimension would have to be attached to all three axes as processed can evolve in all three, as processes can evolve in all three. The point is the three dimensions are made out of lines. Time isn't a line, and it isn't attached perpendicularly to the three dimensions. I'm just saying, you're going to use the word dimension to mean something entirely different. So what's the point of having the word dimension? Because you obviously are providing no rules for the definition of what a dimension is. Time isn't a line, time isn't a physical thing, time isn't any of that stuff. It's a function. It's just a fact that the fastest thing in the universe is moving a certain speed. The fact that it's not happening instantaneously means there's time. If the thing could move instantaneously, then all things would happen all at once and there'd be no time. Everything would be over already. Even an infinite amount of things would be completed now. There, it's all done. I'm just saying, you're not going anywhere with this. There's no reason to play these silly games with words. There's three physical dimensions. Three spatial dimensions. Can I say it that way? There's spatial dimensions. Time is not space. Shit. Whatever. I mean, you people just want to believe in the crap. Alright, all three. Meaning time would have to be three-dimensional. Again, it can't be. It's not taking up space. That's what the three dimensions do. They occupy, they define space. Time does not define space. Space has already been defined. It just takes time for things to move through space. Time is just a function in space. It is not a dimension of space. Therefore, I think that time is a point within the XYZ axis. Well, there's just no point. Container for all three of them. It's a function. It's not a dimension, but whatever. But I agree with you that time is a consequence of the three physical dimensions. It's not a consequence of the dimensions. It's a consequence that you can't move distance instantaneously. Therefore, it takes time. Fuck. For example, as soon as I place a point at the position of the three axes, it's introduced another variable called time, i.e. The moment place the point, which can be measured in an infinite number of ways. Well, again, this is pointless, right? I mean, we really know that you're only going to see time when you move something. That's it. You're not going to know there's any time until something moves, because when it moves, it's going to take it time to get there. Alright, anyway, I just hate this shit. Which can be measured in an infinite number of ways. Well, bullshit. But it would lead you to conclude that the time element is within the three axes and not perpendicular in some mysterious way. Although, who stamps the time on the event? Where does the timestamp come from? Do you have any suggestions? There's not an infinite amount of anything, I would argue. So there's no infinite velocity. There's nothing infinitely fast, and there's nothing infinitely slow, I suppose I would argue. And, they already sort of have defined this as like there's Planck constants, which I'm not saying the universe is necessarily. I mean, it works just because once you get small enough, you can generalize from that tiny thing, because no one can ever see the tiny thing anyway. I mean, we could just argue that pixels are made of pixels on a screen, right? I could look at a computer screen and you could say, well, they're pixels. Well, what if the pixels are pixelated? And then what if the pixelated pixels are pixelated? You can play those kind of games and say there's something infinite somewhere. But I'm just arguing that I don't think the mechanical universe is actually bothering with any of that crap, because it's actually made of things like electrons and protons. And so there is some standard time the universe uses, and we're functioning in it. Obviously, we can't make any relative statements. Our relative perspective can't give us absolute knowledge. So we can't see how fast actual time is, how fast the clock is actually ticking. All we can see is that there's a huge difference between how fast the second hand is moving on a watch and how fast I'm spinning my finger. And the two can be different. We can only measure these relative things. We can't make any, so we just established that a certain thing is a mile per hour, and yes, we can't know. It might be. There's no point in saying it might be. We just can't know relative to the actual universe. I don't even know how to say this in some other way. The fact is, it works very well in understanding there's a relationship between distance and time. And yes, if you expanded the universe, that is, you doubled the size of the universe in an instant and moved everything commensurately, then time would be twice as slow, and you wouldn't notice it. But why would I waste time thinking the universe wastes its time, making itself bigger all of a sudden and smaller, and then makes themselves really big? And then why would I waste my time thinking that's how the elemental universe works? There's no reason to think it does. You're just imagining things again and saying, because I can imagine it means it's realistic. When of course it isn't. I can imagine all kinds of silly stuff. Hippopotamus with the head of a duck and the tail of a wildebeest, and the human feet. And, I can make all kinds of stupid ass shit. Doesn't mean it can happen. Anyway. So that's sort of an industrial, I don't know if anybody's even going to understand your comment, but whatever. I don't even think it's appropriate to the video, frankly, but whatever. All right, Hall. Heisenberg uncertainty principle is a consequence of the wave-like nature that small particles have. No, it isn't, asshole. So again, this isn't a very complicated argument. You have no evidence for it. So you're making some sort of assertion that there needs to be a wave somewhere in here. There doesn't need to be any frickin' waves. And it's just the facts that we can't see it. Again, so you're saying, yeah, the place where all the magic is the places we can't see. God made the universe that way, so we couldn't see any of the magic functions. So yeah, no magical stuff happens in the big universe, but all of the magical stuff does happen on the little universe we can't see. I mean, that doesn't sound contrived and like a pile of shit. I mean, how convenient, that your magic verse hides all of the functions in the places we can't see. How convenient. I mean, you're just making the rules of the invisible man. I mean, totally, yes, unfalsifiable, made up rubbish. So as I pointed out before, this is really a momentum argument, and that the more you know the momentum, in the sense that the more you collect the entire quanta of the energy, the more you eliminate any irregularities or possibilities. So the more, it's exactly like sort of the opposite. So the argument is the less I get of this momentum, the more likely it is that it went this way or this way or this way. So the idea is there's you could almost say a cone you could make, right? And as we get further and further from me having complete knowledge, we get more and more, we get a bigger and bigger cone, all right? And it has a bigger and bigger surface area. So we have more and more uncertainty of where the object went, if it went on that line. So the bigger I make, so the smaller I make one thing, the bigger I make the other thing, kind of like thing. So the less I know about the real momentum, the bigger this cone gets. So the bigger my uncertainty about which direction it went. If you get my point. The fact is, we know the momentum. That one we know. We just don't know the direction. And so they're making this thing like the two things are tied to each other. No, they're only tied to each other by the fact that, well, we can't know, because the electrons travel in these cones. And so there's this tiny little point in the center where we can get really lucky, where we get all the momentum. Well, then we're done with being uncertain. But everywhere else, we're stuck in this cone that gets bigger and bigger. So the less momentum we collect, the less forward momentum we receive, the more uncertainty we have. So I don't know how to put that in his terms, but so the simple argument is, it's to illustrate how simple the fundamental interpretational argument is. Their argument is that as light travels through a hole, let's say, their argument is it gets more and more uncertain, because the size of the hole is making it so I know if the photon went through here, I know more about its position, right? These positions are much smaller than all these positions. So this has less position information. So this has more, greater sign. This has more position information. This has less position information, right? But the trick is, right? So the argument would be is that we know that these holes will create diffraction. That is, there'll be a lot more diffraction from this hole than there will be from this hole. Okay, so that's that cone getting bigger. And so the simple argument is I'm arguing to you people that what makes any light diffract is this surface. The surface is causing the light that bends, because there's electrons there, lots of them, and it hits those electrons, and that's what's causing the light to bend. And obviously, when I make this thing much smaller, I'm more likely that the photon hit the surface. or was close to a surface. So I can't put anything through here without it being very close to a surface, where here I can put things through and they're not very close to the surface. That's the obvious circumstance. So I'm hitting more electrons by guarantee the smaller I make the hole. And so I'm creating a bigger, a wider cone of possibilities. So, but their argument is that this is some sort of rule, that somehow in nature they don't want us to know position and, it's not velocity, direction, yeah, where it's going. And that's just silly. It's a silly interpretation. There's just some, oh, this is just some magical thing that just says automatically that we know too much about its position, so it has to make its direction obscure in some way. And again, this goes back to them being able to run anything backwards. When you run things backwards, they can make up any path for this to get there. And that's the fact that makes their system so stupid, because they're basically saying, well, we don't know the path because this is all randomized. That nothing goes in the middle, nothing goes by the edges, everything just gets randomized. So how could you even reverse it? Where logically you could know that if you actually got a photon from here, you know that it probably did have to come from the source, and it's just the fact is you just bent it a bigger angle because it hit more electrons. You just hopelessly want to believe in the woo. Simple explanation. Alright, it's just photons and electrons, but even atoms and molecules. Let's see. I don't know. Let's do that again. The principle is a consequence of the wave-like nature of small particles have. Well, there's no wave-like nature, so it's just horseshit. It's not just photons and electrons, but even atoms and molecules. So again, just more you say so. Your evidence sucks. The uncertainty principle means the more you know about the momentum. So it's just, like I said, just recite the verses from the Bible. The less the position, and vice versa. And for physical reasons, not for your silly wooey reasons. Where's your evidence of any of this uncertainty in the path of a photon traveling billions of miles through space? Anyway, momentum means you are looking at a wave. So where did you get that from? So again, where's the, this whole argument? There's no waves in magnets. There's no way. What's the frequency of a magnet then? You're sort of obligated to explain to me what's the frequency of a magnet. What's the frequency of an electron as a charged object? You're arguing it's blinking on and off? Horse shit. The position is the particle. Well, duh. It's not the it's not that something is a wave and a particle at the same time. Well, that doesn't make any sense at all. You just said it's all a wave, and now you're saying it's a particle. I mean, you can't see that that's just completely incoherent mush? Alright. It isn't. It's not that something is a wave and a particle at the same time. It isn't. So you're saying it's a wave and then it turns into a particle, and you think that's realistic mush. I think that's just so fucking silly. There's no reason to believe it. There's a physical explanation. I don't need this nonsense explanation. You get different answers depending on what you ask. Well, show me that. The observer. Oh, here we go. The observer crap. I might block you because, yeah, if you're one of these people who thinks you're making the moons orbit the Earth with your brilliant little consciousness, you're such a silly fuck. The observer is involved in the things he studies. No, we can interact with stuff. We can push into it. We can stick our hand between, the water can be coming out of the faucet. We can stick our hand in there. We can only physically interact with the universe, asshole. Alright, this is what separates quantum mechanics from classical physics. Well, just fuck you, I say. I mean, what a pile of tripe. So you didn't provide any evidence for any of this crap, so I'm removing it. It's about making an argument, shithead, that has something in it, some way that you're proving it. You haven't proved any of this Heisenberg bullshit. It's a silly explanation for a simple process. Let's see. I saw Sabine's video and you really made it more comprehensible to me. Thanks for that, dude. Well, fuck you. I'm not a dude. I mean, really, do you people who do this duty thing really think it makes sense to sit there and... I mean, if I really just walked around and talked about you people like you were little dudes, you would appreciate it? I mean, you don't even know when you're being offended and insulted. It's like a black guy being called a boy. I mean, this is just such bullshit. Anyway, I do have my channel. I will be grateful if you take a look to any of my videos, and would be greater if you commented something in them. Tell me what you think. My videos are based on a Mayan calendar. So you think I have any use for that crap at all? As well as DNA photograph. Wow, I'm sure there's lots you can learn from a photograph of a DNA molecule. That both I decoded and both relate to one another. Well, I don't fucking think so. No fucking chance, Bubba. It's just everybody's nuts. Here, speaking of the drunken nuts, here we go again. If a fuse before the Big Bang, so there's nothing. I don't do Big Bang videos, asshole. You must know that. You really must. Was infinitely long, then how did the Big Bang happen? Well, it could be infinitely long in the wrong direction. You know, I mean, the part you have to make infinitely long is the attached part. And somebody lit the fuse while you're still making your infinitely long fuse, then the Big Bang could happen, couldn't it? Whatever. If I had to wait in an infinity long, that's that British suck-ass word. What do they call it? Q. Yeah, Q. Spelled with 5 fucking letters. Q? Why don't you just put Q? Shit. Let's spell out the word Q. Alright. Then I would never get served. I don't even... You know what? I don't even want to read this. Okay. Before the Big Bang is infinity, and after the Big Bang is infinity. There's no beginning and no end. And where did you read this? What book of brilliant knowledge did you get this from? What shred of evidence do you have for any of this horse shit? Oh, that's right, you don't have any. Ugh. And so then Alex says, so reincarnation, I don't know how she got there, is inevitable because there will be an exact copy of this universe again. Who knows? It might work that way, as sad as that is. Oh, man. All the animal habities. Oh, the animal habities. Yes, it's a Hindenburg, over and over. Not to be stuck in an endless cycle. Thanks for the reply. Well, no. Nobody should reply to these moronic conversations. Just, you people, you just can't get it. It's just hopeless, really is. You're just so stuck in your little wacky, wooey notions of reality. I won't hide you yet, but I'm going to delete your horse shit. It's fucking... There's no... We don't do guesses about what happened 47 million trillion bazillion light years ago. We just don't bother with that here. Because guess what? None of you people have a telescope that fucking good. Yeah. I mean, just fuck this bullshit. Oh, I know what happened. Billions and billions and billions of years. You don't even know what's happening right now in front of you, for fuck's sake. Ugh, God, I just hate this planet. Alright, aesthetic pleasure is very addictive to me, but sometimes you see something that makes the ugliness of nature hit home. I don't think this is really related to the video, like when I saw Komodo dragon rip a fawn out of a live deer and swallow it whole. Yes, it's just all a bunch of fun. Did you see it in person or what, like a videotape? Okay. I think the more insidious one is Komodo dragons don't really, they don't usually just, grab stuff and eat it. What they do is they bite it, and their mouth is so full of bacteria and crap that the thing dies, 2 weeks later, and then they eat it. That's pretty hideous. I mean, nature sucks. This planet sucks. People suck. I mean, it's just suck everywhere. I should put that on the cover of my physics book. Suck everywhere. Except it's a push universe. Yeah. It might look like suck everywhere, but it's really push. And pushes suck. Anyway. Push sucks. Yeah. Well, anyway. Words. Absolutely useless. Vocabulary. Useless. Everybody wants to change words into all kinds of bullshit. Alright, so what was I going to do? Well, maybe I'll take a break and then I'll do what I was going to do. I should be back. Make sure I don't screw something up. Alright, so I have been thinking. There's still a dilemma. There's always a few little dilemmas, problems in theories. So this connection between charge and magnetism is interesting. Like, I can illustrate two charges, or I could illustrate north and south, and I could sort of point out how if I created these two things, in a reality, that I could get these monopoles and dipoles to behave the same. So if I could actually put charges really right next to each other, that they would behave the same way as magnets do. So whatever is going on is it's not just a parallel force. I mean, you gotta logically think it's probably the same force. The trick is that magnets don't do much to charge surfaces. So say if I charged a surface like a balloon, okay, and I got a bunch of negative charge on it. The trick is that I can't just take a magnet, alright, and get much of a response out of that balloon. So I can't just take a magnet and say balloon come, balloon go. What actually ends up happening is the charge ends up charging the magnet. And so you have to sort of understand that charge is something that only sticks to the surface. The balloon doesn't charge. The whole balloon doesn't charge. Just the surface charges. So you can put, it's like just saying you can put extra, see, I'm not actually sure about the whole number of electron thing being the right answer, but let's just say electrons do go on the surface. And so if I charge it, I'm just putting extra electrons on and because those extra electrons are there, they're sort of a shield against the proton. So you don't see the proton because there's a bunch of electrons in the way, blocking it. So the electrons are stronger because there's more of them. So in a sense, even though the atom looks proportional, like it has plus in the middle and minus on the outside, it's like having a magnet that would be like having a big north end and then a little tiny south end. So in a sense, it's a very uneven mechanism. It's ions. So ions are intrinsically uneven magnets. So we can't make an uneven magnet, so we don't have any experience with that. But it would behave very differently than a balanced magnet. But anyway, so the point is the charge is collecting on the surface, and the magnet is the whole thing, the whole magnet. All the matter in the magnet is creating the magnetism. So they're all aligned. So it has to do with density. All right, so it's a dense thing. So you could think of this as like being a 1.5 volts, but times a big giant density argument, where this would be 2,000 volts or 200,000 volts, but it's only a tiny density, a tiny fraction of the density of the magnet. So, it's a way of thinking of it. Well, anyway, the point is this is sort of my argument is that we have these two colors of force, the red and the blue. We'll just make them straight lines and squiggly lines. And so this would be a reflective circumstance, right? So we're saying that this, say if this was the north end, it should repel this negatively charged object. And it doesn't really, okay? I mean, as a practical matter. And the problem is because the magnet is made out of metal, So it can acquire a charge. It can be charged. Its surface can charge, and it will move charge really easily. So it'll move the charge all around its surface as it becomes charged. Well, it'll actually become charged on one side and uncharged on the other. That's what metal does. So I didn't say that exactly appropriately. The idea is that this is negative, and what it's going to do on the surface of the magnet is it's going to push the electrons down and bring the, so it's proton exposed. So it's going to reduce the number of electrons on the surface. And by reducing the number of electrons on the surface, it's essentially changing the magnet, right? So the magnet has a nice order of north, south, north, south, north, south, north, south, north, south, north, south, going up here, right? North, south, north, south. And all of a sudden it screws it up by putting another north on there or whatever. So now it's essentially blocking the magnetic force it's killing the magnet by essentially putting paint on it. So if you thought of the magnet as being a flashlight, shooting light out, the extra electrons are essentially, blocking what the magnet's doing by changing the atom's arrangement and negating the ability of the magnet to continue doing that. So instead of the force coming out, it just reflects back in, and probably there is a little bit of increased magnetism coming out the sides. So the magnet, as you bring it towards the charged object, is probably excreting more magnetism out these sides than out these ends, because you're doing this to it. And if I turn the magnet, the same phenomenon is going to happen. I'm going to again break the magnet in the direction of the charge. Magnet's not working anymore because I've painted over that part with like reflective paint, and so now there might be more magnetism coming out of these ends. So anyway, the interesting thing I'm looking for but have not been able to find at all is so if anybody can find experiments, where they just take two neodymium magnets or whatever and put a charge on them. So let's just say this was the north side and this was the north side. No, we don't want two facing magnets. We want it the other way around. So this is south, this is north, and this is south. So they're attracted to each other, and then you charge them both negative. What's going to be stronger? The negative charge that's going to force them apart, or the magnetic attraction? And so I haven't seen anybody. So you can just tie them to strings here, right? Just tie them to a post, the two magnets. All right, then bring them, a little post here and a little post here. So have them attract to each other. Then place 200 volts on each, 200,000 volts on each one. And what happens? Do the two magnets push in? Do they push out? What do they do? So I've never seen any charge experiments where they actually charge a magnet. And even if you just took a magnet and charged it with 200,000 volts, right? I mean, give it a good charge. 20,000 will probably be enough. All right, so I put 2,000 volts on it, and I insulate it. It's on a piece of glass or whatever, so it's insulated. I charge it. Does it stay charged? And will it, can I put a little paper, a little tester around it and see what does it do to the little tester? Is it acting as if it's charged? So these are interesting experiments. I just haven't seen anyone do them. So I would be very curious how strong the charge force is versus the magnetic force. See, unfortunately, it's really humid here where I live because the house is not really heated and a lot of other things, blah, blah, blah. Poor people, kind of sucks. And it's a basement, and so I have very little chance of doing good charge experiments because charge just leaks into the humidity and I'm fucked. I just don't have space either yet. And so if somebody, who fiddles with things, just charge a couple of magnets, see what they do, because I can't find it anywhere on the internet. And it's like I said, it is this. I'm arguing, yes, it is the same force. It's just the trick is that all magnets are metallic. They can seem like they're not, like refrigerator magnets can seem like it's not metal. Well, yeah, it's really metal bits inside there. There's iron inside. and the iron is screwing the magnet because the iron's creating this surface phenomenon that's breaking the magnet. So anyway, so it doesn't work. But see, that it's always attractive. Everything always, charges attract anything that's neutral, because it basically charges the neutral thing to the opposite charge it has. Because, like I said, if this has got a bunch of electrons excreting electron force, well, then it's going to push the electrons off the surface and expose the protons, so to speak. So it's always going to go positive, negative, if it's neutral. And even when they're not neutral, the stronger charge will tend to push, the negative, how do you say, it'll convert. Charges like to convert other things into their opposite. They like to, well, see, the stupid image comes to mind of two men coming towards each other, and one of them is going to try to turn the other one into a girl, But yeah, that's what they tend to want to do. Anyway, I think that's enough, probably. Yeah. So, anybody has anything on charge and magnetism in terms of experiments that really, deal with actual charged objects, not electrons moving and all that kind of stuff, because that's a little more complicated. That usually has to do with what kind of gas you have in the tube and all kinds of other things. So I'm not even sure they're electrons, frankly. It's like Stern-Gerlach. They talk about it like it's an electron experiment when it's an atom experiment. Well, a lot of these cathode ray tube kind of stuff might just be a force experiment, not an electron experiment. Because there's still enough gas in there that you're actually just hitting atoms with accelerated force. Not accelerated, just force. With gamma rays. You hit atoms with gamma rays, you're going to see some photons. Anyway, so enough said. Till the next time and such. Yeah, just really curious. So, that'd be all.